Hi everybody, welcome back to the Feynman technique. Today we're going to tackle this integral right here. Again, got this off the channel Maths 505. I've just been kind of on a kick where I go through all his integrals and then see if I can solve them a different way. I'm pretty sure this is going to be solvable with Feynman integration. I'm not sure how he solved it. I'll check it out after this video, and I will also link to his video in the description. But let's just go ahead and get started. All right, so the first thing I'm going to do is I just want to see what this looks like. All right, so there's our graph right there. That's what this function looks like, and we're going from 0 to 1. All right. So, well, the first thing that jumps out at me, obviously, is that this natural log can be broken up into two separate natural logs. And then probably what I'll do is I'll replace this with a parameter t. So right away, let's let f of t equal the integral from 0 to 1 of the natural log of 1 plus tx plus x squared over x dx. All right. And then we will note that well, what's f of 0? I believe, well, f of 0 is this. So I believe that is some form of pi squared. But let's go ahead and figure it out. Okay, so let's see. I'm going to let u equal x squared, implying du equals 2x dx. And then to make that x dx, I'm just going to put an x here and another x downstairs. All right, so now, and let's call this integral j, and we'll label this one I. Okay, that means that j, using that substitution, is going to equal, well, bounds of integration are not going to change. This x dx becomes a du, this x squared becomes a u, and this x squared becomes a u. All right. Oh, I forgot something. We actually need a 2x dx, don't we? Yeah, 1/2. There we go. So this should be actually 1/2. All right. And we'll just make sure that that actually is f of 0. It is. Okay. All right. So how do we solve this one? I think what we'll do again is just let some w equal 1 plus u. All right. So, well, I'll say that's dw equals du. So j is now equal to, let's see, this is w. Let's see, u is going to be w minus 1, and du is dw. Oops. Yeah, w. There we go. Okay. Oh, I forgot to change my bounds of integration. You know what? That's not going to work. No substitution. All right. So how are we going to do this? Well, let's use a series expansion. Oh dear. Okay. So 1 over x plus 1, we know that that's the sum as n goes from 0 to, and I'm just going to put 10 in here, of negative 1 to the n times x to the n. And that's good from 0 to 1. You can see if I extend this out, I'm sorry, negative 1 to 1. We extend that out. Yeah, so we can say that this is infinity. So this is true. Now I'm going to go ahead and change our w variable here to x. Okay. So this means if we anti-differentiate both sides of this, we are going to get natural log of x plus 1 is equal to the antiderivative with respect to x of this. That's going to give us n plus 1 here over n plus 1. And then we'll just make sure that that lines up. Yeah, that's going to work. Okay. We'll put this back to infinity. And that means that this is equal to this. We can get rid of this. And then we can go ahead and set our j equal to this, except our natural log x plus 1 is just going to become this. And let's go ahead and just make sure that that is actually going to converge to what we want it to. Yeah. Okay. All right. This 1 over x can come inside the sum as an x to the negative 1, making this just x to the n. All right. Let's see. And then, of course, we can switch the bounds of integration and summation. And again, I just want to make sure, yeah. All right, so j is now equal to this. And I actually, what I should have done is I should have put a plus c here. Don't forget, I technically did an indefinite integral to get this, so I should have put plus c and then let x equal 0 to get that c is equal to 0. But I knew that would happen, so I didn't bother doing that. Okay. So now we need to evaluate, well, hold on. Let's just bring this outside and then put that like that. And check again to make sure that that's converging, that I haven't made any mistakes. All right, and then we evaluate this. This is going to be x to the n plus 1 over n plus 1 from 0 to 1. That's just going to be 1 over n plus 1. So we get negative 1 to the n over n plus 1 squared. And again, I'm just going to check that. Now this, let's see, let's add 1 and then subtract 1 from all our n's. So if we subtract 1 from that n, that just introduces a negative sign. All right. So this is the alternating sum of the reciprocals of the squares, half of that. And I believe that is pi squared over 12. So the whole thing should be pi squared over 24, and it is. So we can just say that this is pi squared over 24. So all that just to find our f at 0. Now, to continue with our Feynman integration technique, we can also say that f at negative square root of 2 minus f at negative square root of 3. And it occurs to me that I could have put a minus sign here, but I didn't, so we'll just go with it. And that's gonna give us I. All right, so we'll copy this up here and save that for later. All right, now we'll differentiate this with respect to t, using the Leibniz rule for differentiation under the integral sign. So we have f prime of t. Well, let's see. We're going to get 1 over this thing. And then times the derivative of this with respect to t, of course. That's just going to give us an x. So we have 1 over this. Now, this is an integral that is definitely solvable with traditional techniques. What you would do is complete the square and then solve it from there. a lot of steps. I don't want to actually do that. So what we're going to do is we are going to plug this into the integral calculator. All right. So we'll refresh the page here and plug that into our integral calculator, integrating from 0 to 1. Sorry about my barking dog. All right. So from 0 to 1, that gives us this junk right here. Okay, so we'll copy that down here. So f prime of t is equal to this. No. No. It looks like integral calculator got that one wrong. All right, so what I'm going to do, I could solve it myself, but I just don't want to. I'm going to pause the video, and I'm going to plug it into ChatGPT. I'll be right back. All right, it looks like it's finishing up now. Okay, that looks more like what I would have expected. So, online integral calculator is getting some wrong lately. Let's go ahead and plug this in. We'll see if that actually lines up with our f prime of t. All right. So, 2 over the square root of 4 minus t squared, 2 over the square root of 4 minus t squared, and then parentheses, arctangent of t plus 2, t plus 2 over this. And then, let's see, minus arctangent of t over that. Yeah, there we go. All right, so that's our f prime of t. Well, oh my goodness. I don't know if this was the right way to go. I mean, I'm curious if that can even be anti-differentiated with respect to t. We're going to go ahead and try the integral calculator one more time, because that would just be bonkers to try to do, if it's even doable. I just want to see if it is. Let's see. Okay. Well, it says that it's equal to this, but it is, oh yeah, it might be. Okay. So now we have to solve for our constant of integration c. Okay. So integral calculator was able to handle that. Okay, so we're going to use this. That f of 0 is equal to pi squared over 24. But that's also equal to this when t is 0. So if t is 0, this is just going away. And if t is 0, we get, let's see. Oh, don't forget plus c. Plus c. If t is 0, well, get a 0 here. This becomes a 2. This becomes a 0. This becomes a 1. Arctangent 1 is, of course, pi over 4. So this becomes pi squared over 16. Get rid of the squared. This 2 cancels this. That becomes negative pi squared over 8. We'll change this to 3 pi squared over 24, and then add it to both sides. So that's going to give us pi squared over 6. C is equal to pi squared over 6. All right, let's see if that worked. Should have. Yeah, okay. So, all right. Let's plug in t is equal to all that stuff. All right, so we have this. I is equal to this. So I is equal to this minus, and then we'll put a parentheses, this. And now let's go ahead and zoom out a little bit. We don't need that graph anymore. Can we zoom in? Yeah, there we go. All right, so what's going in here is, oh, well, first let's notice that this pi squared over 6 and this, oops, what did I do? And this pi squared over 6 are going to go away. All right, and we'll distribute this negative sign. Oh, no, not yet. Not yet. What we want to do is plug in negative square root of 2 into all these. All right, so negative square root of 2. And I'm just going to do this step by step very carefully. All right. So then negative square root of 3 goes in to these t's. Yeah, okay. So that is correct. Now let's clean this up a little bit. That negative is going to go away. This is just going to become a 3. So this is just going to become arctangent of negative 3. All right, what's going to happen here? Again, this is just going to become a 1 in the denominator, and we will get 2 minus the square root of 3. Let's see, what's going to happen here? We are going to get a 2, so we're just going to have negative 1. All right, and here we are going, this is going to become square root of 2. And then we can multiply the top and the bottom by square root of 2 to give us a 2 here, a 2 here, and a 2 square root of 2 here, and divide the top and bottom by 2. And rearrange it like this. Okay. You know, I am not sure what arctangent of square root of 2 minus 1 is. I suppose we could use double angle identities. Let's just see. It's going to be maybe pi over 12? No. Pi over 8? Yeah, it's pi over 8. Okay, so we could have used double angle identities on that to figure that out, but we have Desmos, and we all know we could do that, so let's just do it the fast way. So arctangent square root of 2 minus 1 is pi over 8. Yeah, I have to replace the entire arctangent. Whoops. All right. Okay, we know what arctangent negative 1 is. That's negative pi over 4. So this is going to become a plus pi over 4. All right. So this is, let's see, this is going to be a 4 over 16, and this is going to be a 2 over 16. That is going to be an 8 over 16. So, wait a second. Pi over 8 plus pi over 4. 6 pi over 16, 3 pi over 8. 3 pi over 8. Okay, now let's figure out what this beast is. All right, again, we could use double angle identities. But since we have Desmos, let's see, that's going to be pi over 24. 12? Yeah, that's pi over 12. All right. Let's see, we'll replace this with pi over 12. Arctangent negative square root of 3. I should just know that one, but I don't. Let's see, that's pi over 3. That's negative pi over 3. All right, so we'll copy this here. So that's going to become a plus pi over 3. So that's 5 pi over 12, or 5 pi over 6. 5 pi over 6 once we get rid of this 2. Oh, no. I did a dum-dum. Okay. Yeah, that is 5 pi over 12. And then this actually becomes 144. And this becomes a 25. This becomes a pi squared. This squared goes away. This becomes a 72. And this becomes a 1. All right. And then this negative will distribute to become a positive. We can get rid of all these parentheses. This is going to become a pi squared. It's going to become a 9. This is going to become a 64. We can get rid of the squared. This will become a 32. And then we can put this over here like this. All right. So now I'm going to have to find the common denominator. All right. So let's write 32 as 2 to the 2, 4, 8, 16, 2 to the 5th. So that's 2 times 2. Well, we'll just write 2 to the 5th. All right, and 72 is, let's see, that's 2 times 6 squared, but that's actually 2 squared times 3 squared, and this is 2 to the 3rd. All right, so let's figure out what's missing. Well, all we're missing here is a 2 squared. So let's do 2 squared and bring this up to a 2 to the 5th. And what we're missing here is a 3 squared. So we'll put a 3 squared up. 3 squared. That's actually going to become a 3 to the... we'll just call this... We know that this is 81. All right, 2 to the 5th is 30, let's just see what this is. That's 288. 288. 288. And then this is a 4, so that's 100. 100 minus 81 is 19. So 19 pi squared over 288 is the answer. All right, guys, that was a long one, but I hope you enjoyed this, and we'll see you next time.